I would like to go over the remaining problems from the incompressible flow week. These are the in-class problems. The second problem on that is on the homework, so I'll just give a blurb about that at the end. And the third problem deals with model scaling and Reynolds effects. And you essentially have a wing that you would like to design. So this is a full-scale wing. The full-scale velocity is 35 meters per second. It has some chord C, CF, full-scale chord, and you're going to test this in a wind tunnel and achieve full dynamic similarity. So, thinking in terms of drag, we have our drag coefficient. Again, it's a function of alpha, Reynolds, and Mach. This case here, the full-scale wing is below the incompressible limit of Mach 0.3, so we can ignore Mach effects. So in order to achieve dynamic similarity, we have to hold these constant. Thus, the Reynolds and alpha of full scale will match the Reynolds number and alpha of angle of attack of the model scale. If we do that, if the alpha and Reynolds are fixed, then we will have a simple relationship between the drag coefficients on the model and full scale, that they will namely be equal. And recall that our drag coefficient is the drag normalized by the dynamic pressure and the planform area. The model is half scale, so that we have the chord of the model is equal to 1/2 the full scale chord. And again, we're going to have to match alpha. Model will have to be equal to alpha of the full scale, and Reynolds of the model will have to equal Reynolds of the full scale. What are the implications on this second equality? We have, I'll write this out more explicitly, we have the velocity on the model times the length scale, and remember the Reynolds number that's appropriate is the chord, divided by the kinematic viscosity is going to equal the full scale velocity times the full scale chord divided by the kinematic viscosity. I didn't give subscripts to the kinematic viscosity because in this case we're assuming that the flow properties in the tunnel match those of the full scale. If that were not the case, you'd have to consider the differences in kinematic viscosity. For this case, the numerators have to be equal, and this tells me that the model scale velocity in the tunnel is going to have to equal UF times the ratio of the full scale chord to the model scale chord, which is known as lambda. That is essentially the model scale, or the inverse of the model scale. So, and in this case it's 2. The ratio of that is what the question is posed. The chord ratio is 2, so I'm told the model velocity has to be twice UF. Looking at the definition of the Reynolds number again, a velocity scale times a length scale divided by a kinematic viscosity scale. If kinematic viscosity is fixed, if you reduce the chord, then you're going to have to increase the velocity. So we find in the tunnel, what was my original velocity? In the tunnel, 35 meters per second full scale, this tells me that the tunnel velocity is going to be 70 meters per second. So one concern is the tunnel velocity now fast enough that we have Mach number or compressibility effects coming into play in the model, whereas they wouldn't come into play on full scale, and we don't. We're not quite at that velocity. So this is okay, although it's getting close to not okay. The second part of the question asks, what is the ratio of the drag on the model to the drag on the full scale? So the model is smaller, so that we might surmise that the drag is less, but it's also subject to a higher velocity. The densities are assumed to be the same. So we have the drag on the full scale is equal to the dynamic pressure of the full scale, U full squared, times the planform area of the full scale, times the drag coefficient. And the model drag is 1/2 rho U model squared, dynamic pressure of the model, times, and I should write CD full here, times the planform area of the model drag times the drag coefficient of the model. So these are just the individual forces. We're converting back from non-dimensional to dimensional. But since we've used dynamic similarity, these are the same, so these are eliminated. We've assumed rho to be the same, and of course half is the same. So we're left with this ratio right here. The ratio of full-scale velocity to model scale velocity is a half. So here we have UF squared over UM squared is equal to 1/4. What is the ratio of the full-scale wetted area, or sorry, planform area to the model scale? SF over SM goes as C, the quarter of the full scale squared over the quarter of the model scale squared goes as 4:1. So we have a 1:4 because of the dynamic pressure ratio, but we have a 4:1 because of the area ratio, the planform area ratio. So we have for this case that the drag of the full scale is equal to the drag of the model. Obtain this dynamic similarity. This is not always the case with model scaling. If you're matching Mach, you would not come up with this. If you're doing ship testing, you do not come up with this. It's just a particularity of this Reynolds scaling, assuming that the flow properties are the same. But it does go to show that you may be dealing with significant forces in the wind tunnel if you hope to achieve full dynamic similarity. In reality, it's unlikely you're going to get the model, particularly a small model. The smaller the model is, the faster the flow velocity has to be relative to full scale. If you have a 4th scale model, it's got to be four times the flow velocity, and maybe dealing with compressibility effects. So in reality, you may not be able to match the Reynolds number. And this goes to the other short lecture I put up, demonstrating that for the case of lift, at small angles of attack, the Reynolds, you may be able to work with Reynolds insensitivity, meaning that if the model scale Reynolds number is smaller than the full scale, and that is likely the case, that the lift coefficient is still going to be quite close to what you would expect if you were able to achieve full dynamic similarity in the tunnel. And so these kind of scaling problems are issues. They are very big issues, and they have to be dealt with. The drag coefficient in particular, if you're thinking about frictional drag, it is highly dependent on the Reynolds number. If you can't match the Reynolds number, then you can't match the frictional drag coefficient. So you may be in a situation where you have CL of the model is approximately the lift coefficient of the full scale, even if Reynolds model is not equal to Reynolds full scale. But this does have the assumption that you must maintain the same angle of attack, and that you are really in that linear range of Reynolds numbers, and that your Reynolds numbers are not significantly different. But you will not have that the model drag coefficient due to friction will not be equal to CL, a CDF frictional, because that's highly dependent on Reynolds number. This is skin friction, I should write. The other components of drag, which we'll get into throughout the semester, one is what's called a viscous pressure drag, or a separation drag. That case may be somewhat Reynolds number insensitive, with some caution, depending upon the points of transition and how bluff the body is. The third component of drag, which we'll discuss, is the 3-dimensional drag, the wingtip vortex drag, which we call induced drag. And this induced drag carries the same Reynolds insensitivity that we discussed in that prior lecture. If things are attached, if flows are attached and we're at mild angles of attack, then the lift that's created and the induced drag, which is associated with that lift, can be related to that lift, can both be considered Reynolds number, Reynolds insensitive, I should say, with some caution. So you may be able to say CDM equals CDF for the induced component. So it is very possible to study wings and the properties of wings in flow tunnels, even if you aren't able to maintain the same Reynolds number, if in fact you you are in this particular flow regime, which is where the focus of the work is. And we will look at, when we get into transonic flow, we'll return back to the idea of how do we deal with the Mach number effects. If you're looking at transonic or supersonic aircraft, the Mach number effects are large, if not the dominant effect on the flow field in terms of both lift and drag. And there you may just discard Reynolds and focus on achieving the same Mach number.